Iodide ions are oxidized to iodine by peroxodisulfate ions. The reaction can be catalyzed by Fe2 plus ions. Write a half equation for the oxidation of iodide into iodine. So I need two of these here, and then I'm going to need 2 electrons on this side over there. Part B, write a half equation for the reduction of peroxodisulfate, so that's S2O8 2 minus into SO4 2 minus, so SO4 2 minus. So my redox element in here is sulfur, so I'm going to need to balance that first, so I've got that there, and then let's just check. So I've got 8 oxygens on the right, 8 oxygens on the left. So all this balances. I just need to get the electrons on. So on the left hand side I've got 2 minus. On the right hand side I've got 4 minuses. So I need 2E minus over here. And then part C, write an overall redox reaction. So I've got 2 on the left, 2 on the right here. So I can just add these together. So 2I minus plus S2O8 2 minus goes to 2SO4 2 minus plus I2. Okay, part D. In this experiment, to investigate the uncatalyzed reaction of uncatalyzed reaction, the concentration of iodine was determined at different times, shown by curve A. Curve B was produced with the same volume of iodine as was used to produce curve A, but with a different concentration. What change was made here? So obviously it's less, but if you kind of look at what we've got here, so 1, 2, 3, 4, 5.5 up to here, going to 1, 2 and 3/4 thereabouts. So the concentration has halved here. Okay. Part 2. On the axis given, sketch a curve to show how the results will change if the experiment leading to curve A was repeated with the presence of a catalyst. So a catalyst speeds up the rate of a reaction, but it comes out unchanged. So that means that this is going to have to be steeper, but it still needs to finish at the same point here. So steeper, so there it is going steeper. And then here it is reaching that same point here all the way to the end there. Okay, so there's 2 marks for that. 1 mark for the curve being steeper over here, 1 mark for it finishing at the same point as A. And then part 3, suggest how the student could have determined the concentration of iodine at different times during the reaction. The easiest one is by colorimetry. Remember, iodine is brown in aqueous solution, so the browner it is, the more concentrated it's going to be. And of course, you do a calibration experiment for that first. So by colorimetry, or you could talk about quenching and then titrating with thiosulfate. Okay. Part E. In a different reaction, the rate equation for the reaction between P and Q at a given temperature is that. So use the data from experiment 1 to calculate the value for the rate constant. Right, so rearranging that rate equation, so K equals the rate divided by P and then multiplied by Q squared. So I've only got one row that I can use here, and that's row 1. So putting those values in, so 9.45 times 10 to the minus 4 divided by 0.76 multiplied by 1.22 squared. And if you work that out, that is going to give you 8.35 times 10 to the minus 4. And then deduce the units. So the units here, so I've got moles per decimeter cubed per second on the top. And I've got 3 lots of moles per decimeter cubed per second on the bottom. So the one on the top will cancel with 1 on the bottom. So that's going to leave me with mole minus 2 dm6 seconds minus 1. Okay. Complete table 2. So there's a couple of ways that you can complete table 2. You can use this and rearrange that equation to get the values here, here and here. Or you can use what's going on in the rate equation in order to do this. So there's no big easy thing going on here though, I have to say. So the easiest way really is to rearrange the equation, use k. What you'll get for experiment 2, plugging k into that with p and q here is 3.19 times 10 to the minus 3. And then rearranging it to get p on its own, and then plugging the values in would give you 0.569 here. And then rearranging it to get q on its own, not forgetting to do the square root of it, would give you 3.05. Okay. So calculate the initial rate of reaction when the concentration of P is doubled and at the same time the concentration of Q is halved. So the concentration, so P is doubled and Q is halved. So let me go back up to here. So that is doubled and that is a half, which is a half squared. So what I need to do now is take this value here, times it by 2, and then times it by a half squared, and that will give me my rate. So let me do that down here. So 9.45 times 10 to the minus 4 times 2 times a half squared, because that one is second order, and that gives me 4.725 times 10 to the minus 4.